Hello everybody, this is Cam with Danomics, and today I'm going to be bringing you another Danomics Basics video. In this video, we're going to look at how you can calculate permeability for your rocks. Permeability is one of the holy grails for petrophysics. Trying to understand, how your reservoir is going to flow is, incredibly important. Permeability is also a very challenging property to evaluate. It's only gotten more challenging in recent years as we started looking at unconventional systems. And the reason for that is once you start introducing a frac to the system, then we have questions about, oh, are you looking at the permeability of the rock? Are you looking at the permeability of the entire system post-frac? Um, Now, as petrophysicists, we are mostly focused on what's the permeability of the rock, of the reservoir before it's stimulated. And the reason for that is one, our tools are doing the measurements before the stimulation. So when we go in and we measure porosities and saturations, we're measuring those with wireline before the wells have been completed. Also, when we measure the core that we've collected, which serves as our source of truth, as our calibration, we are measuring that, of course, on unstimulated rock. So it's only natural. That's what we're trying to calculate. Now, when you're dealing with, these ultra low permeability systems, this can, you know, it can be exceedingly challenging to even measure the permeability in some of these. So with today, what we're going to do is we're actually going to focus on what I like to term as a tight conventional. So this is a lower porosity sandstone, and we are going to be looking at these tight conventionals and really try to dial in the permeability on them. So before we are ready to approach permeability, we should have already done our interpretations of both the porosity and of the saturation in our system. If you've not yet done that, or you're not sure on how to calculate the porosities and saturations, I'd encourage you to go back and check out those specific videos on calculating those properties. So now moving forward, we have already performed our mineral inversion, which has given us our porosity. We've gone through and we've evaluated our picket plots. We've looked at the formation temperatures and salinities, our M and N data, and we have determined our water saturation. Now, we want to make sure that we're calibrated with respect to those properties as well. And we're going to bring in the core. And we bring in the core and we see that, in this case, we've got a really good match in most cases between our porosities and our saturations to core. We can see maybe we're getting a good, better fit in some areas. Maybe we're a couple of percent off in other areas, but in general, we have an excellent calibration here. So now that we have those calibrated, we're ready to attack the permeability. So when it comes to calculating permeability, there are a number of options that are out there. Within Danomics, we have 5 methodologies available for you. Uh, all of these methodologies are quite similar. So all the researchers and workers in this area have taken a very similar approach with these methodologies. 3 of them are essentially identical, and these are the Timmer, Wyllie Rose, and Tishier variations. In all of these, the formula that we have for calculating the permeability takes the form of some scalar P times the porosity to an exponent Q divided by the saturation taken to an exponent R. So, all of these methods depend on you having calculated your porosity and your saturation correctly. So if those are wrong, your permeability is going to be incorrect. So that's why it's important to get those correct first. The other 2 methods that we have in here, which are Heslop and Coates, are similar, but they're slight variations. Ken Heslop's formulation, which he derived looking at the Alberta Basin, is P, so that same scalar, times the effective porosity taken to an exponent times 1 minus the water saturation, so times the hydrocarbon saturation to an exponent R. And the Coates formulation is once again a scalar P times, this time, our effective porosity taken to the Q. And then that is multiplied by essentially our effective saturation taken to the R. So Coates was trying to remove any excess permeability that may have been calculated due to non-movable fluids in the rock. So that's the difference between those methods. Now they're all quite similar. They all have the same number of parameters that we need to set, but remember they are different formulations. Some of them use percent, some of them use decimal for the various inputs. Now we handle all that for you in Danomics, but the parameters will need to be adjusted for that. Today we're going to focus on using the Wyllie Rose methodology. So with permeability, it's always good to have a source of truth, and we're going to want to use our core for this. So first thing we need to do is we need to add our core here. So we're going to bring up the settings here. We're going to add points. I believe this is called perm here. We're going to say our permeability and core. And then we need to set our scales, and it looks like we're going from 0.001 millidarcies to 1 millidarcy here. And now we have our permeability on here, and we need to put that in log scale. We always measure permeabilities on a logarithmic scale, and that's how we display them. So now that we have that, we can see that we've got our permeabilities here, and the first thing that we immediately see here is that using the parameters that we see out of the box, we are drastically overestimating permeability. Now that's not a surprise because these are quite old methodologies, and the parameters that these researchers established on their empirical data sets were measured typically on good quality conventional sandstones. So first thing we want to do is try to get a better initial calibration here. And to get that calibration, the first parameter that we're going to adjust is this parameter P. Now P it's just a scalar. You're just moving your whole calculation left and right here. So if we make P smaller, what we see is that it shifts our calculated permeability to lower values. And what we'll do here is we will adjust P until we are in the ballpark. So the initial value, just as a reminder, was 25. That was the parameter that Wyllie Rose came up with. We're going to need a value that's significantly smaller than that. So we tried 5, we tried 2.5. We can try a value of 1, see where that gets us. Okay, that's getting us closer. Maybe we want to go a little bit lower than that. And this gets us in the ballpark. We're not quite there yet, but let's stop there and then see what we can do with some of our other exponents. Now we have the exponent Q. Now as a reminder, in the Wyllie Rose formulation, this is P times phi to the Q over SW to the R. So let's see what effect Q has here. So if we make Q a lower value, that shifts our distribution higher. And if we make Q a higher value, that shifts our distribution lower. Okay? So And unfortunately, there's no way to really measure these variables. These are variables that we need to find through exploration here. So, you know, there we go. We have a pretty good estimate there with a value of 3. And when we look at the R variable here, once again, we see this is SW to the R. Now let's take a look at how this parameter behaves when we move it lower. This will shift our results lower. When we move it higher, it'll shift our results higher. So this works opposite of Q. And finally we can try to dial this in to get the best match that we can. And so it's through adjusting those exponents that we are trying to get our match here. And so what we're looking for is we're looking to get a match. Now this is an excellent match. I typically wouldn't expect a match of this high quality, but this is what we are seeing in our data. Now, why is it important that we get our saturations and our porosities correct? Well, let's see what happens if, let's say we've set this on one well, and then let's pretend we've, that we didn't have this this saturation control points. If we were to, go with a more, out of the box set of parameters for M or N in this case, what we'd see is that maybe, we would be underestimating our hydrocarbon saturation here, so our water saturations are too high. Due to how these equations work, that means our permeability is then too low. So, that shows you the importance of being calibrated not only on, for porosity, but also for saturation as well. So it's worth, spending the time to get your porosity and saturation correct instead of just coming straight in and looking at your permeability and calibrating to that. So I think it's a very important order of operations here where you want to calibrate to your porosity, you then want to get your saturation calibrated, and finally you want to calibrate your permeability. And then once you've done that, now you're going to have a very powerful petrophysical model that you can apply across your well stock. And then you can take that off to build your reservoir models, so your reservoir engineer can then understand the expected performance, how much oil, how much gas are these wells going to be capable of flowing. All right, well, I hope this video was useful to you. And if you'd like to learn more about any specific topic, just let us know in the comments, and we will we'll try and make some content around that. All right, thank you, everybody. And if you want to dive into this yourself, you can always do a free trial at www.danomics.com. Thank you.